exiting to top, you'll see it's just a bunch of particles acting stochastically. Quantum mechanics, it might have several words, but no one can deny the fact that quantum theory works.
In this video, we're going to talk about the solid-state devices, and more specifically the diode and your transistors. Now, when it comes to the actual knowledge of the content of this video, you don't need to know the content, most of this content for HSC in terms of your actual exam, but it'd be really good for you to know in general because it's just how these different machines operate. So you need to have some knowledge of how they operate, but you're not going to be asked, for example, to explain how the transistor works in your HSC exams. So I'll show you first how the diode works. Before we do, we want to make sure we talk about the NP junction again. So your NP junction and what happens when we combine the N and the P-type semiconductors. So this here is our N-type semiconductor. And what happens when we add the N-type semiconductors to the P-type semiconductor? We actually join them together. Remember, I said beforehand, that these are actually neutral. So when they're by themselves, they have a neutral charge, which means an equal amounts of positive and negative charge of the N and the P-type semiconductor are neutrally charged, so same amount of charge. I mentioned that the blue ones were the blue part here, this is your P-type semiconductor, and your pink one was your N-type semiconductor. The reason why is because these blue holes are meant to represent your positive holes, and your pink dots are meant to represent your free electrons. So these ones would be your phosphorus that have your free electrons, and the ones which are blue are your boron, for example, your group 3 elements, which have extra positive holes. So when we joined them together, both sides were neutral, which meant equal amounts of positive and negative charge. But now that we joined them together, we're going to have something changing, right? The reason why is because these free electrons will move over and combine with these free positive holes. And when that happens, we call that recombination. So you might have heard that word before, recombination. When that happens, we have charge appearing. So we go from it being neutral to it being charged. And I'll go through what that means or why that would be the case. So you can imagine this part down here to represent this part. So this part here is the same as this part here. It's meant to represent something called the depletion zone. So this in gray here is your depletion zone. And I'm going to cover why that's called depletion zone. The reason why is because here we used to have these positive carriers. Right? We had the positive holes and the negative electrons. But what happened to those is they actually recombined to form those holes. Right? So here we've got the phosphorus, which is meant to represent these ones here. These are the phosphorus. Here's our boron, which are meant to represent these ones here. And what happened when we joined them together is we had phosphorus having one extra electron, this one there, and boron having one extra positive hole. Now, this electron actually crossed the other side and recombined with that positive hole. And what that meant is we had no more positive hole, that one electron had left the other side and had recombined that positive hole. And now what we have is this boron has an extra electron. Beforehand it was neutral, it was no charge, but now, because it's an extra electron, it will be negatively charged. Right? So it's going to have a negative charge, an overall negative charge, so the extra electron. And that phosphorus used to have more electrons, it lost its electron, so it has one more positive charge and a negative charge, which means now it's going to be a positively charged ion. So here we have a charge being created, and what happens when we have a charge being created? Well, we have an electrical field being produced. So because of those charges, which are meant to be represented by these ones here, these 6 here, so 3 pluses being equal to 3 of the phosphorus, and those 3 minuses being equal to 3 of those borons, they don't have their charge carriers, so the charge carriers are gone. What I mean by that, it would have been those free electrons or the free positive holes. Those charge carriers are gone, they're depleted, which is why we call it the depletion zone. But what we have now is we have these charged ions. So these are the charged ions. They were neutral before, and now we have the charged ions by themselves. And what that means is that at that position, we have the electrical field being produced. And this electrical field is defined as it goes in the direction of what a positive particle or a charge would experience. So a proton would be deflected in this way. This would be a proton being deflected in that way, a positive charge, for example, a proton. But a negative charge would be deflected in the opposite direction. So negative charge would be deflected in this way. So electrons are experiencing a force in this direction, from the left to right. And what that means is that these electrons, which are still there, so there's still some electrons left behind the depletion zone, they want to be able to cross the other side, right? They want to be able to cross there, but they can't. And the reason why is because the electrical field is actually pushing them back. So they're trying to, but the electrical field is pushing them back, and they're stuck where they are. So as soon as this electrical field comes about, and it comes about because of depletion of charge, as soon as that comes about, these electrons are stuck. They can't move. So current cannot flow as soon as the electrical field is being produced, because this electrical field in this case is preventing it from happening, electrons changing sides. Right? This is what we call the NP junction. So the NP junction is when this happens, right? When we have electrical field being produced, when we combine the N and P type semiconductors. That's the first thing you should know. The next part is what happens when we apply a voltage to it, right? We've got two scenarios. One we call the forward biased, and you often see the symbol for the forward biased looks like something like this. It's a bit of an arrow, then there's a bit of a dashed line, and like that. So this is the forward bias symbol. And then we also have the reverse bias. Now what does all this mean? Forward bias and reverse bias. Well, what that means is for the forward bias, we have the P type, this the end, the terminal, this terminal here, being from the P type connected to the positive end terminal. So positive connected to the P type, whereas the negative terminal, this terminal here, is connected to the N type side, right? So that's what we call the forward bias. And what happens when we have the forward bias is now we're going to have your electrons, right? They leave from the negative side, they go to the positive side. That's what electrons do. Electrons are flowing this way. Electrons are flowing this way. And your positive holes will be going the opposite direction. So positive holes are going this direction. Now what that means is pretty simple. You're going to have electrons passing. You're going to have more electrons being pumped from this direction. They're going to move this direction. They're going to be pumped in from this side. So you're going to have more electrons moving past here towards that depletion zone, lots of electrons. And the other side, you're going to have lots of positive holes moving this direction and moving towards also the depletion zone, right? So you're going to have lots of positive holes here. So again, imagine this end here. This our problem came about because of the electrical field being produced between the N type and the P type, right? So the electrical field was in this direction. It was going from the positive charge on this phosphorus to the negative charge on the boron. And we want to remove this electrical field. If we can remove the electrical field, that means we can have electricity actually flowing. But in the way we've connected this circuit and we've applied voltage to it, that means that we're going to have many more electrons coming this way. So I'm going to draw electrons coming this way. We're going to have electrons coming this way, and we're going to have positive holes coming the other way, right? So we're going to have positive holes approaching from the other side because of the way we've attached everything. What that means is that here we have a positive charge. That means we have one less electron than we used to have. But now, because we have extra electrons, what that means is that these electrons can jump back into where they used to be, right? The position where it used to be. And that means we remove our positive charge because we've got our electron back. So I'll show you the electron jumping. Right, so I'll just grab this electron, has jumped back into where it's meant to be, and we can find it here again. Right? So the electron is back. We've got 5 electrons in that shell, and everything's perfect. Right? So phosphorus is back to how it used to be. Now this boron had an extra electron. That was its problem. It had too many electrons because it gained an electron. But now one of these electrons will be attracted to the positive hole, which comes from the back, and it will jump into the positive hole. So you're going to have one of these electrons, this one here, let's say this one, will recombine because it's moved to that positive hole, recombine with the positive hole, and thereby disappearing. And that means that the boron has got back to its original position, which means it also has no more charge. The charge also disappears. So now this is neutral charge again, the boron. So is the phosphorus. there's no more charges. So what that means, if there's no more charges, that means the electrical field will also fall away. Right? And that means that we have electrical field falling away. So I'm going to draw this electrical field arrows being gone. I'm going to redraw the positive holes reappearing because of the way that the connection between the circuit has made that possible, plus the electrons reappearing, so everything is neutral again. And what that means for the actual flow, it means that these electrons which are coming from negative and wanting to go to the positive can now keep going. They can keep going this way. And the electrons will end up going from the negative to the positive, and current will flow because the electric field is gone. So current can flow in a forward bias situation. So current can flow. Whereas in a reverse bias situation, we have basically the opposite happening. In the reverse bias, what happens is we have the negative terminal being connected to the p-type, whereas the positive terminal is connected to the n-type. So it's the reverse of what happened beforehand. And what that means is you're going to have electrons moving from the negative to the positive. So electrons are moving this way. Electrons are moving this way. And you're going to have your positive holes going the opposite direction, from the positive to the negative. So what you can imagine is we have more positive holes reappearing on the back side of the n-type semiconductor. So here you have your positive holes reappearing. The other side you're going to have more electrons reappearing. Now what that happens is these electrons will be moving, and they will actually be recombining with these front positive holes, these ones here. What that means is they will recombine and they will make these front positive holes disappear. And these, on the other side, you have these positive holes. What they will do is they will recombine with the electrons, these ones here. And when they recombine, they make the electrons disappear. And what that means is these electrons are gone. And as you can see, in the one example, we decreased the size of the depletion area, but now we have more depletion. More of these charges are gone, which means the depletion zone will actually grow. So I'm going to show this growing by just drawing this grayness, which means that all the charge carriers are gone. We've got more depletion zone. We have more positive negative charge ions. We have more of these ions, charged ions. And what these charged ions will do is they will produce an even more powerful electrical field. So in the first example, the forward bias, we removed the electrical field, which was good. In the reverse bias, we have a much stronger electrical field. So the electrical field now is much stronger. And what that means is that these electrons which are left over here have absolutely no chance, have no chance of getting to the other side. It's just more or less impossible for them. The depletion zone is too big. What that means is for the reverse bias, we have no current flowing. So what you should get out of this part is we've got two different types of, these are called the solid state diodes. A solid state diode is more or less just your NP junctions connected with a voltage. So we have voltage applied and current flowing through these NP junctions. Now we can apply it two different ways. Either we have the positive terminal connected to the p-type and negative connected to the n-type. That's what we call the forward bias. Or we have negative connected to the p-type and the positive connected to the n-type. That's what we call the reverse bias. And the forward bias we have current that can flow, whereas in the forward bias we have current that can flow, whereas in the reverse bias we have no current that can flow. That's the gist you should get out of this part. And that's how a solid state diode works. Now, next part is the solid state transistor. Again, you don't need to know how this works. It's not really important because you're not going to be asked a question of how exactly this works, but it's still good to kind of understand the gist of it overall. So for this, you should know that there's two circuits. There's a small circuit which starts here, flows through the emitter, and flows through the base. I'm going to cover those words in a second again. And then goes to the positive terminal. This is the first circuit. Call that the small circuit. The other circuit starts here. It goes for the emitter, goes for the base, goes for the collector, and then goes for the resistor, and back to the positive terminal. This is what we call a large circuit. Right, so two circuits, a small circuit that goes through the actual, we call it the emitter, so E for emitter, that was this part here, and it also goes for the base, so emitter plus base was this part here in the middle, And the other one, which is the large circuit, goes through the emitter, the base, and the collector. Right, so large circuit goes through the E for emitter, B for base, and C for the collector. Now, what you should know is, or what's good to know, is if there's a small current that flows through here, so a small current that flows through the small circuit, what that allows us to do, it allows us to basically destroy this electrical field which builds up from the N to the P part of this junction, so this part here. There's an electrical field here, which basically means electrons can't pass. Remember, this electrical field, in this case, what that means is these electrons are trying to pass through, but this electrical field, which is built up from the N to the P, always builds up from the N to the P, what this electrical field does is it will actually block the electrons. It's going to work against the electrons. The electrons want to go that way, but it's going to push them back down. It's not going to be able to allow them to pass. So we need to have some way that we can destroy this electrical field, first one, this one here, to make sure the electrons can actually pass. And we do so by applying a voltage. So by applying a voltage, apply voltage to small circuit, If we apply a voltage to a small circuit, that means the electrons can actually pass. Electrons will always go from the negative, so they're going this way. They want to be able to go through here and go through the emitter to the collector. That's where they want to go. But if we apply a small voltage to the first small circuit, that means that we're going to destroy the actual electrical field, just like we talked about when it comes to the forward bias, the same mechanism of how it destroys it, right? Or how it weakens it. But what that means is we have removed this problem here, this part, so these charged ions, which means this electrical field is also gone. So now your actual electrons can pass through this part. It can go from the emitter to the base, and then it can actually even go further. And the reason why is because there's a electrical field which works in the opposite direction, right? Electrical fields always go from the N to the P type semiconductors. So the electrical field is going this way, and in this case it's going the opposite direction as it was beforehand, right? So this part here is making the electrical field go the opposite direction. So what that means, it will actually propel the electrons. So the electrons will be going faster in this direction. Electrons are being propelled into this direction. So as soon as they get past the first part, the second part, they're actually going to be accelerated. They're going to be moving faster. Right? So once they get past the first part, and they go into the main circuit in the second part, here they're going to be moving faster because of this electrical field. Here they're going to be accelerated. And then they're going to move into the main circuit and then cover this part. So once they get past here, they'll cover the rest of it. But what this allows us to do is, for example, if we have, let's say this is part of a mobile phone, let's say mobile phone, and let's say we have an incoming signal. Now if it comes from the air, it's quite quiet. This might just be like this, a small signal. And we want to be able to hear that. So our mobile phone receives it, but we can't really hear it yet because it's too silent. So what can actually happen is it can go, this small radio wave goes and hits our phone, and it's converted into current, right? So this signal is converted into current. That means now the signal itself is going to flow in the form of electricity. It's going to flow this way. Electrons are going to flow this way. And so what's going to happen is just what I described earlier. First, because this current is flowing now, we're going to have the actual first electrical field being broken down. That means they're not going to be blocked anymore. And then the second electrical field will propel them to go even faster. And what that means is that once they get past here, they're moving at faster speed than they originally were. And they're going to meet the resistor. The resistor is where we have a new signal being produced. So this was the original signal. And what we're going to find at the resistor is that signal is going to be looking similar, but it's going to be bigger. It's going to have the same kind of shape, but it's going to be bigger. And what we call that is we call it the amplification. This was amplified. So now it's just louder. It's the same voice. If someone said something, it's the same voice, but just louder. Right? And that's how the transistor converts a silent signal to a louder signal through this mechanism. Again, you don't need to fully understand the mechanism, but you do need to know that transistors allows us, for example, to amplify signals. And just with the way I described now, again, don't need to remember that way. but it can also act as a switch. So it can act as a switch because if, for example, there's a really big current coming through this side, through the big circuit, there's a large current coming through here, but there's no current coming through the small side. If there's no current here, so no current through the small one, then there won't be any signal. So if we want to shut out a signal, if we want to shut it down, all we have to do is we make sure we have no current flowing in the small one. That means the electrical field won't be gone. That means we won't be having any signal being sent from the large circuit. Right? So it can act as a switch by having no current being sent through the small circuit, or it can act as an amplifier. If we have a current flowing through the small circuit, whatever current is flowing through the small circuit will be amplified in the larger circuit. So it'll be the same signal, just louder. Right? That's how the amplification part works. So you should know that transistor works either as an amplification device or as a switch, that we can switch things on and off. That's what you should get out of this part. And you should also remember what we talked about when it comes to your forward bias and your reverse bias and your solid state diodes. It'd be good to kind of have a conceptual understanding of that part and to understand what the NP junction is all about. Right? But I hope that was useful.
Thank you for watching.